Welcome to notes 8.1 and 11.1. We are going to be talking about polygons and their interior and exterior angles. And we're going to start by talking about the interior angle sum theorem, which you derived in the activity. And basically it states that the sum of the measure of the interior angles of any polygon is the number of sides minus 2 times 180. Please make sure you have that memorized. And then the exterior angle sum theorem is even easier than that because it says no matter how many sides a polygon has, the sum of the measures of the exterior angles is 360. So no matter how many sides, altogether, those angles add up to 360. So here are some examples of the sums of the interior angles of a polygon, and this should look a lot like that table that we used to derive it. Basically it says if I have a triangle, it's got 3 sides, which means that the number of triangles that can be formed inside it that don't overlap is the number of sides minus 2. So obviously in a triangle you can form one triangle, and then you take that and you multiply it by 180, and that is the sum of the measure of the interior angles. In a quad, it has 4 sides. You can form 2 triangles, and when I take 2 and multiply by 180, I get 360, and so on. And that holds true for any polygon. So let's do some. What's the name of an 8-sided polygon? If you said octagon, you are correct. So to find the sum of the interior angles, I take that 8, I subtract 2, and I multiply it times 180, and what do I get? I get 1080 degrees. A 9-sided polygon is called a nonagon. And I take 9 minus 2 and multiply it times 180. And what do I get? If you said 1260, then you are right. How about 10 sides? What's that called? That's a decagon. And so 10 minus 2 times 180 gives me 1440. And finally, what's a 12-sided polygon called? Is a dodecagon. And I take 12 minus 2 times 180, and I get 1800 degrees. All right, that's how the sum of the interior angles works. Here's how we can use it to solve for a missing angle. So first I need to decide how many sides my figure has. So let me see, it's got 1, 2, 3, 4, 5, 6. So I'm going to figure out the sum, which is 6 times minus 2 times 180, and that will be equal to all of the angles added together. So x plus 120 plus 100 plus 140 plus 150 plus 120. Please go ahead and solve this for x. Come back when you have an answer. Hit pause now. And you should have gotten that x equaled 90 degrees. So we've been talking about what all of the angles equal when you add them together, the sum of the interior angles, but now we're going to talk about how to find a single interior angle. And we need to know the measure of each interior angle of a regular octagon. And it says, hint, what does regular mean? Well, what does regular mean? It means that all of the angles are congruent and all of the sides are congruent. So for us, what that means is if I know what the sum of the interior angles are, and I do because I can just take 8 minus 2 and multiply it times 180, and if the angles are all the same, then, and there's 8 of them, I can just take that sum and I can divide it by 8. And when I do the math on this, I find out that it is 135 degrees. So what would the formula be to calculate each interior angle? Well, if we go back to our formula for the sum was n minus 2 times 180, and all we did was divide it by n. But I think there's an easier way to do this. If you'll remember, no matter how many sides an exterior angle has, All right, no matter how many exterior angles there are, no matter how many sides a polygon has, all of the exterior angles sum up to 180 degrees. And if you'll remember, an exterior angle is simply an angle that extends off of my polygon in one direction. So because these two are a linear pair, they are supplementary. So whatever this one is, if we call that x, this one is going to be 180 minus x. And it's much easier to find this one because for this one I just take 360, which is the sum of the exterior angles, and divide it by however many exterior angles there are. If it's an octagon, there's going to be 8. Well, 360 divided by 8 is 45 degrees. And then to find the interior angle, I just take that 45 and I subtract it from 180, and I wind up with 135 degrees. So that's just an alternate way of finding the measure of an interior angle of a regular polygon. This only works with regular polygons. Okay, let's see what you learned. I would like you to solve these two problems for me. Keep in mind that this one down here, these equal signs actually are not necessarily there. There should be 71 degrees and 112 degrees and 135 degrees. We do want to know what x equals, but I don't know why the rest of these equal signs are there. So solve these problems for me. Come back when you have an answer. Hit pause now. Okay, so in this one, you should have set it up something like that, and you would have gotten that it was a nonagon. And in this one, x equals 42 degrees, because there are 4 sides to this, and you would have added these all up and set them equal to 360. Please go ahead and solve this one. Tell me what x equals, and come back and check once you have an answer. Hit pause now. All right, you should have gotten that x equals 133 degrees. If you didn't get that, you may have forgotten f. Sometimes when the number's not written there, kids forget to include it as part of their, or one of their angles that they're going to sum up. You may have also noticed that I skipped over example number 3. I'm going to ask you about that one in the notes check. Now we're going to change gears a little bit, and we are going to talk about special right triangles in regular polygons. And there is a formula that will help you find the area of any regular polygon, and it is the area is equal to 1/2 the apothem times the perimeter. Some people say this apothem. I like to call it apothem, you know, because it's the only North American marsupial. Anyway, cheesy pun, sorry. Okay, so let's talk about what the parts of this formula stand for. Well, I just told you that A meant apothem, and P stands for perimeter. So what is the apothem? Well, an apothem is the line that connects from the center of the polygon to the midpoint of the side. And it is the perpendicular bisector of the side and a radius of the inscribed circle. So if you look at my pentagon up here, I've got an inscribed circle, which is blue, and then I've got a circumscribed circle, which is red. And my apothem would go from the center of both of these circles, because they both have the same center, to the side of the polygon, the midpoint of the side of the polygon, which means it divides it into 2 congruent parts. And it is therefore a radius of this inscribed circle. And since it is the midpoint, it also happens to be the perpendicular bisector. So it is perpendicular to the opposite side. So this line right here, that is my apothem. And then I'm going to talk a little bit about R, because even though R doesn't appear in this formula, it helps us find the parts of this formula. So R is known as the radius. And when I mean radius, I'm talking about the radius of the circumscribed circle. So it's the radius of the red circle up here. And it connects from the center of the polygon to the vertex of the polygon. And it also bisects the vertex angle. And it's the radius of the circumscribed circle. So if I were to draw the radius, it comes from the center of the circle to the vertex, and it bisects this angle right here, right, cuts it into two congruent parts, and it is the radius of this red circle. That's why we call it radius. And so you can see that I've got a right triangle formed here. The third side right here, that is my half side, right, because it's half of this whole side right here. So I can use these three pieces. I can use the Pythagorean theorem to find any of these three pieces that I need. And once I know what the half side is, I know what the whole side is, and I know what the perimeter is, and that's how I find my area. Let's actually do some examples and you'll see what I'm talking about. In three regular polygons, the triangle that's formed by the radius, the apothem, and the half side is a special right triangle. So if I look at my square here, which is the first of the three, there's my apothem, there's my radius. Let me label those. So apothem, radius, half side. Well, the special right triangle that's formed, let me draw that, is a 45, 45, 90 right triangle. Because this radius bisects this vertex angle, it means that this is a 45-degree angle right here. So this is a half side, this is my apothem, and this is my radius. And so it's a 45, 45, 90 right triangle, and you remember that the pattern for that is x, x, x radical 2. Well, my apothem is one of those x's, my half side is the other x, which means my radius is x radical 2. In an equilateral triangle, which is the next regular polygon that has a special right triangle inside it, when I draw my apothem and my radius, remember that my radius bisects this angle. Well, if this is an equilateral triangle, this is a 60-degree angle, which means that this part right here is 30 degrees. So when I draw my triangle that forms, I have, this is a 30-degree angle, this is a 60-degree angle. This was my radius, this is my apothem, right? These are right triangles, and this is my half side. So this pattern was x, x radical 3, 2x. In this case, my apothem is x, my long leg is my half side, so it gets the x radical 3, and my radius is the hypotenuse, so it becomes 2x. The last special right triangle that forms inside a regular hexagon. Here's my apothem, here's my radius. Now, the triangle that forms with this one, let me draw a triangle here. If you'll remember, we can find the measure of each interior angle by taking the number of sides minus 2 times 180 and dividing it by the number of sides. And in this case, this has 6 sides. So when I work this all out, I find out that that's 120 degrees. Each interior angle measures 120 degrees. So if this bisects that 120 degrees, then this right here measures 60, and this measures 30. This is still my apothem, this is still my radius, and this is still my half side. So what makes that significant is that now my half side is the side opposite the 30-degree angle, so my half side gets the x. My apothem is opposite the 60-degree angle, so it gets the x radical 3. The hypotenuse is still r, so it is still 2x. So these are the patterns that form inside only these three regular polygons. All other polygons, you've got to figure out some other way to find the apothem and the perimeter. But in these three, the special right triangle will help you do that. All right, these notes have gotten very long, so we are going to practice all of these patterns in part 2 of the notes. Join me there.